Our next speaker is Michael Franz, and Mike has been with us for longer than I have been, I guess. So it's been a long,
20 years,
about 20 years or so, whatever, close to that. As you get older, you kind of, these things become phased out. So if you think of mobile code or just-in-time compilation and Java, the way, so we're changing gears. From deep learning, we're going to now hardcore software, computer science in that sense. So if you think of just-in-time compilation, mobile code, one of the prominent names that comes anywhere you kind of look, wherever you look, is Mike Franz. And the work started from his PhD, which was a fantastic kind of piece of work that happened. And slowly he's been chugging away at this compilation and mobile code for a long time. Actually, if you use, I think, Mozilla Firefox,
yes.
Is that correct? There's a piece of, I think it's called Trace. Are you going to talk about that? Or?
So I can just briefly say that, yes.
All right, so he will tell us a little bit about that as well. So you'll find his code, which is kind of inside that, and it's used by, obviously, anybody who uses Firefox. So it's had a huge impact. Today, I think he's going to talk about something which has been bothering him or exciting him for the last 4 or 5 years, maybe, or maybe a bit more, which is in biologically inspired software defense and code diversity and so on. So he'll give a talk on that thing. One more quick thing, he just told me, so I'm going to mention it anyway. So one more message behind his talk is, his point is that PowerPoint on phone is better than the PowerPoint on a laptop. So you should judge and let him know if that's true or not. He's trying to convince me that that's the case. He's using his cell phone for doing his projection.
Okay, so yeah, I'm a compiler guy, and I'm sure you've all used compilers.
I feel like coffee while you speak.
Okay, and so originally I've been working in just-in-time compilation. A few years ago, I actually basically talked the then CTO of Mozilla, Brendan Eich, who was also the inventor of JavaScript, into putting our JavaScript compiler into Firefox. And the main reason why he probably agreed is because there was no competition. Nobody else had a JIT for JavaScript in Firefox. And the weird thing was all the browsers at the time had Java JITs, but no JavaScript. Nobody realized how important JavaScript really was. And there were all these big things coming along, like Gmail and so on, that were all very heavy in JavaScript. And, well, you can say the rest is history. So then all of a sudden Google came out with Chrome, and Mozilla Firefox would probably have been dead in the water if they hadn't had our little JavaScript JIT at the time. Perhaps in recognition of that, the grad student who did it with me, who later went to Mozilla full time, is now the CTO. So he's taken over that job. So there's 5 former students of my group in Mozilla. The garbage collector in Firefox also comes out of my research group. Today I'm going to talk about security because, so there's 2 different things going on in my group. One thing, we're making things faster, which is something that compiler people usually do. That's going to be much more important as, Moore's law is basically sort of going to stop dead in its tracks pretty soon. We have maybe about 3 more generations left, and then all of a sudden, hardware is not going to be able to give you any more improvements. So everything that you'll have to do is going to be in software. So if you look at companies, lots of companies are building compiler groups. Facebook, even Disney is building a compiler group because they need the back end to do their rendering on server farms, and they basically have human compilers right now translating the little what the artist did in languages like Python to C, which can be compiled efficiently. And the second thing that I'm doing is security, because it turns out that it's really the programming language people that are causing all the security bugs the problems in the first place. And one of the things is that we have all these nice languages, and nobody uses them, right? Not at least for the infrastructure stuff. So if we would all build our browsers in nice languages with full type checking and so on, we wouldn't have any of these security vulnerabilities. But people are still using C and C++, and this creates job security for security researchers. So we could even say that the left side of my lab is creating the problems for the right side of my lab to solve. So what is the problem with these secure software vulnerabilities? So there's this wonderful little word critical, and critical is actually Microsoft speak for a bug that allows a bad person anywhere in the world to completely take over your computer and own it. So critical is something actually really severe. And unfortunately, we have lots of these bugs regularly in software used all over the place. And the deeper question is, are there people who know about these bugs? And if you've been paying attention, to the Snowden revelations, for example, you know that there are people who know about these bugs. And unfortunately, this looks like trivial and old because it's been around for a long time. But unfortunately, we still have these bugs, and some of these vulnerabilities exist for very long times. So, for example, in 2009, a vulnerability was discovered in the Linux kernel that actually survived 2 kernel versions. So this bug was around for 8 full years, and nobody saw it. This whole idea about the open source idea, there's so many people looking at the code that someone's going to find a bug. Well, for 8 years, nobody did. And note that Android is built on top of Linux too, right? So there's huge numbers of devices that were left completely open to anyone who knew about this. We have interesting vulnerabilities. So this is a Microsoft security bulletin from last year, a year and a half ago. And they had the bug in a core library. But then if you look down here, you can see all these products that use that library. All of these were vulnerable. We've got Adobe. Adobe is very good for having bugs that really affect a lot of people. So here I have a Flash Player vulnerability that affected Windows, Macintosh, Linux, Solaris, and Android. So basically everyone. And potentially allow an attacker to take control of the affected system. Means everything on your machine is owned. And even better, it's being exploited in the wild. So bad guys were already at it. So that's not a situation you want to be in. And it's not just computer software. So this is an interesting bug. This is probably the most interesting thing that happened in the last 3 years. So Cisco managed to have a vulnerability in the software stack on their IP phones. And this vulnerability allowed basically a third party to take over the phone. And the problem with these phones is there's no physical off-hook switch. So you could actually turn on the microphone and listen to what's going on in the room. And the Cisco initially said there's a little green light that comes on when you pick up the receiver. Unfortunately, it turns out that that's also a software function. So there's no hardware function that ties the microphone to the phone. Now, where's this phone installed? You probably have it. We have it here, that exact model in our labs. It turns out that this is a board Air Force One. That's the phone. You may have seen these phones, and they're all over the place, right? So this is the situation room on board Air Force One. This is the desk of the president in the Oval Office, and you can imagine that's not a good idea if you have a vulnerability in here that allows someone else to basically change the firmware. The people who found this are at Columbia University. They went one step further. They had a cool little thing where they were able to actually introduce a bug, like a listening device. So it turns out that on the PCB of that phone, there is a wire that has exactly the right length, so you can actually modulate it in the FM spectrum. And so they were able to change the firmware of the phone so that it would pick up what's being said in the room and then basically broadcast in FM. So you could stand outside and listen what's being said in the room without, like a classical bug from the 50s, except that no hardware, no access to physical access necessary to install the bug. Beautiful. Okay, so what's new from the old days? What's new is that 10 years ago, 15 years ago, there were like movies about hackers and so on. And at those times, hackers did this for prestige. It was famous hackers and you did this. And what's new now is that you can see here, the best researchers are now motivated more by monetary gain than prestige. All of a sudden, you can actually monetize knowledge you have about bugs. And it turns out there's even things like eBay for bugs. So you can actually, if you find a vulnerability, you can just sell it to the highest bidder. And you can imagine that the bad guys pay more than the good guys. There's actually even price lists. So legitimate business publications have articles in which they have price lists. And you can see iOS actually, this is probably a ranking of how secure are things. So iOS is actually pretty secure. If you find an iOS vulnerability, you can get it between $100,000 and $250,000. It's also, so regular business publications are all of a sudden writing about this market, as if it's just yet another commodities market. And New York Times had an article, hundreds of thousands of dollars that governments pay. And the other interesting thing is that it's very fast from market to application. So this magazine actually followed one of these bugs in Adobe code, and it was basically used within 24 hours of being sold. So very fast turnaround. Of course, the software manufacturers are also reacting to this. So Microsoft, of course, is reacting to this. So they have something called a bug bounty program, where they give you minimum bounties for finding these bugs. And you can imagine that this is the floor on the price, right? So you can get at least that much if you sell it to Microsoft. If you sell it to foreign governments, you can get a multiple of the price that Microsoft is willing to give. And Microsoft even had this prize that was slightly embarrassing for Microsoft, because the winning entry actually was defeated within 3 weeks of them having cashed the check. So the security research is interesting because, unlike many other, in normal research areas, you're competing with maybe Google or other researchers. In security research, you're not just competing with the other researchers, you're also competing with, criminals and and foreign governments who are trying to hack you. So it's interesting. Okay, I'm almost done with the So there's a kid, 16-year-old kid, who's already twice got the prize from Google, $75,000 each. One kid wins against the whole Google engineering team. That's interesting. And then there's this interesting murky area of legitimate government use. So it turns out that the biggest buyers of these vulnerabilities are actually law enforcement agencies, not just in the US, but in other countries as well. So if a court orders a wiretap on your phone today, basically there's no way your phone can be tapped anymore by traditional means, because you're going to do Skyping and SMSing and so on. So what really happens is that the FBI or the LAPD or the NYPD goes out and purchases a vulnerability from one of those little guys who sell them and puts a rootkit on your phone. That's the only way you can do court-ordered wiretaps today. And that's the same in almost all countries. So it turns out that FBI, NYPD are actually the two largest purchasers of these vulnerabilities on the open market. So that's why you hear this thing, when law enforcement occasionally says, "Oh, we don't want, more security," because their job would get more difficult. Okay. So, and then there's the interesting question, how many agents of pick your favorite foreign government work at Microsoft? The problem is we cannot distinguish between a legitimate programming error and something that just looks like an error that has been placed there on purpose. So that's a real problem too. And and it's cheap, right? You can for the price of launching one spy satellite, you can probably put 1,000 moles into software companies. So it's very cheap. So, and then the last question is open source better? So in theory, this idea was always that open source, because there's so many people watching. In practice, we actually have pretty good tools to find bugs automatically, except that they are very expensive to use. So a few years ago, DHS, Homeland Security, actually paid for one full automatic scan of the LAMP stack. That's Linux, MySQL, Perl, and Apache. And it cost about $3 million. Because you need people to look at every single error message to make sure if it's an error or not. So you can't do that. You can't spend $3 million every 3 months as you would have to, because the software is being changed. However, a foreign government doing this on an offensive budget, for them is no problem. So they can just suck down all the open source software and do the analysis to find the vulnerabilities, and that's probably what they're doing. And then the difference between open source and closed source is not really that big, because we're actually having hackers steal the source code from major companies. So for example, Adobe recently said that all of the source code had been stolen. Adobe is on every device, right? So now if whoever stole this does the static analysis to find the bugs, they can spend more money on this than Adobe can, because Adobe doesn't really care that much about vulnerabilities, right? It's not their problem if you that much under current liability rules. So, but a foreign government may be able to use that to their advantage. So So how does an exploit actually work? So there's two things. First of all, the attacker knows about a place in which the program has an unspecified behavior. For example, there's a buffer and nobody checks whether what you feed into it is large enough to fit into the buffer. And then the attacker also needs to know exactly what happens. Even though it's unspecified, it's actually predictable to the attacker. To give you a very, and then randomization is a defense why you make it difficult for the attacker to guess exactly what happens. So let me give you an example. This is very, very simple, JBack attack. There's a code with a vulnerability, if I execute the read, the attacker could try to overwrite the buffer with more. You see I wrote it beyond the end of the buffer, and I actually overwrote the return address on the stack. And now if I execute the return, I'm going to jump to this address here, and I'm going to start opening a connection to the White House. Now that can no longer happen on modern machines, because one of the things that the hardware manufacturers have agreed on is to make the stack non-executable. So we can inject things, but we cannot inject executable code typically. That hasn't stopped the attack, and I'm going to explain why in a few minutes. Okay, so what has been our original idea here? And our original idea was we have a compiler. We're compiler people. So we have a compiler, and we let the compiler generate many, many versions of the same program automatically. They all differ slightly, but they do exactly the same thing. And then, how about running these different versions in lockstep on a multi-core? We have all these cores lying around. One cell phone there has multiple cores, and they're not doing anything productive. They're basically a marketing argument, right? You buy 8 cores because it sounds like better than the 4-core. Even though you have nothing that's sufficiently parallel. And if you run them in parallel, the different versions, we can watch that they're doing the same thing. So for example, one idea, grow the stack in 2 different directions. So I have one version of the program that grows the stack in this direction, one in that. I don't know where my vulnerabilities are. They're still unknown to me. But an attacker, is trying to overflow the buffer. On one of the 2 versions, the attacker overflows the return address, and on the other version, the return address is stored somewhere else. And as soon as I execute the return, now the 2 versions of the program that have been doing exactly the same thing until now are going to start doing different things. And that I can actually detect almost in real time. And I can actually catch the attack in mid-flight. And so we actually got a patent on this idea of using parallelism to detect malicious code injection. And not only that, DARPA is starting a whole big program around this idea. So DARPA has just made available about $60 million for this, and just we, nicely enough, get about $3.5 million of that just here at UCI to do the basic research to bring it to the next level. We meaning just me. And so the idea is, of course, you don't, right now we did this with 2 versions, but you can do much more interesting things, right? So you can do something even similar to RAID. You can have 4 versions and use majority voting to decide which version got infected. And you could even repair things in real time. So let me give you a quick idea. How do you do the checkpointing? Right? So the easiest is to do whenever you have a system call. System calls are the only places where you can actually do something bad, like write or network or something like that. So we could only simply test at system calls, are they requesting the same system call with equivalent parameters? They're not the same parameters because the memory layout and things are different in the versions, but they are equivalent to each other. Or you could do even something smarter. You could have, if I have a multi-core, and even if I have out-of-order execution, I typically have in-order graduation of my instructions. And if I say, okay, so the instruction streams that are running here, they need to do the same thing, but the addressing can be different. And what I need to do is, I can simply have a little extra thing on my processor, and it's not on the critical path. It doesn't matter if this happens a few milliseconds after the thing has already executed, but I can just compare, are they the same, and if they're not, I can raise an interrupt. And the interrupt doesn't need to immediately terminate the program. It just knows, okay, now something's unusual. Let's see what's going on. Right? So, but if you build this, and this is a hardware thing that you could add onto an additional processor, and we've talked to hardware manufacturers about building this, then an attack would actually have to succeed in a single cycle. And that really raises the bar to your attacker. You know, I never say it's impossible to attack this. I'm just saying it makes it much, we're just talking about raising the attacker workload. So a foreign government with unlimited resources, kind of a moonshot, might still be able to do something here, but it would be very, very difficult. And one of the interesting things that we are looking at right now is hardware is actually just coming out with something called transactional memory. Who's heard about transactional memory? So in databases, you have this idea of a transaction. So you can do something, and then you commit, and it becomes permanent, or you can abort, in which case you roll back to the state before the last commit. Now, in processors, we all have caches. And someone clever got the idea, well, you can use this cache just like in a database. You can actually basically say, we're not going to write back the cache to memory immediately. We're going to collect all the modifications in the cache, and then we have a commit operation that makes the cache visible permanently, and we have a rollback. And all new Intel processors actually have this, and it's going to come on big time in the next generation that's out in October. You can actually, you can do lots of probabilistic algorithms very elegantly with this, right? You can do simultaneous updates, and if there's a conflict, then you have to do the slow way, and if there was no conflict, then you commit. Well, you can also use this for having multiple versions of the program run in parallel. So what we do is we run forward exactly the amount that we can cache. Then we check, did they do the same thing? If yes, we commit, and we've actually made progress. If no, we know on this last little chunk of code that ran, there was some problem that is probably a security problem. And even better, because they are actually all doing isomorphic computations on the same data, you can actually even compute what the correct state should have been for any of the corrupted versions, as long as only a minority of the versions were corrupted. So you actually get something that's very similar to a RAID for storage for running processes. And that's something that we're working on right now, and that DoD is really interested, as you can imagine. So we started with this, and this may actually be the true killer app for multi-core, at least on a desktop. And we thought this was really cool. And then people started talking to us and said, well, that's all right. You're completely right. We have all these cores. They don't do anything useful, except we would rather turn those cores off. So it turns out you have your multi-cores, right? And if you look at Intel's processors, they have this weird thing called speed boost. And the processor has two different gigahertz ratings. One is if you have all the cores turned on, and you actually get the higher one only if you turn all the other cores off and run this thing as a single core. And that has to do with power consumption and the way that the chip is actually not spec'd to run all the cores at the high clock frequency. And on a battery-operated device, you really want the battery life, especially if you don't have anything that's really parallel. So people say, well, it's extra hardware that you have to pay, and we may not be willing to do this. So our next idea was very simple. How about crowdsourcing the problem? So instead of running all the different versions in parallel on the same computer, how about simply giving every person in the universe their own private software that is different from every other person's software? So, and it turns out that just at this time, we have these app stores, right? Nobody actually buys software on disk anymore. Maybe the only thing I buy on disk is TurboTax. But everything else, I download from somewhere. So what I could do is, I could actually have a diversity engine, and it just generates a billion different versions of Firefox. And different people who download Firefox get different versions of Firefox. And what we've built is actually a way to hide this, not as only from the end users, but also from the software developers. The software developers write their software, they check it into a version control system, and they forget about it. And error messages, you need to be able to handle crash dumps and error messages. On the way back to the developer, these error messages automatically get normalized so that the developer only has a single view on the software and needn't know that actually what was running was many, many, many different versions. Now this sort of predicates that the compiler is more reliable than the program that the developer wrote, and that's usually the case. Right? Compilers are among the most reliable things that we have. If you think about it, Apple, for example, made a transition from a PowerPC based to an Intel based computer and had an automatic translation system under the hood that actually in real time dynamically compiled the PowerPC code to Intel code. And millions of people didn't even notice that this transition was going on. If you're running VMware, basically a lot of the code that's Intel code actually gets retranslated into completely different Intel code under the hood automatically without anyone noticing. So we have these dynamic binary translation systems that are so reliable that nobody even thinks about it. You have JavaScript, just-in-time compilation all over the place. These are among the most reliable pieces of software that humanity's ever written. Okay, and so what does this solve? Well, it solves many problems. Among others, it actually solves the patch exposure problem. So some of the attacks that we see today are actually generated automatically by analyzing software patches. So Tuesdays, Microsoft has Patch Tuesdays, where they release the fixes for Windows that they've found in the last week, and the bad guys take that patch and automatically create attacks from it. And now you have a problem that the time window between the availability of the attack and when you apply it is critical. Now the problem is that your most valuable users may be the ones who can't get to the patch. If I'm roaming in Europe and my only connection to the internet is a USB stick with a mobile subscription, I'm not going to pay $40,000 in roaming fees to download the patch. I'm going to wait until I'm home. Or if you're in Afghanistan, what's the bandwidth to Afghanistan? Not very good, right? So you have people who can't get to the patch. So what's the cost of doing all this? Well, there's two costs, right? The first cost is that an optimizing compiler finds the best program. And now we can't really give everyone the best program. One lucky winner is by accident going to get the same program that the optimizing compiler would have sped out, and everybody else is going to get something slightly worse. Yes?
That raises the question of generating all these different versions. There's a pretty large cost.
Yeah, so I'm talking about that, yeah. So we actually have our compiler running on Amazon's cloud, and it turns out it costs very little. So basically, it's less than a cent to compile Firefox, which is about 35 million lines of code. So all the software that's on a typical laptop is probably about 5 cents. So that's perfectly acceptable, because it turns out that cloud computing has really gotten very cheap. Okay? And so what's the threat model? The threat model is that we have a bad guy that can do arbitrary code execution, and we actually have adversaries who have time, money, and resources, possibly nation states, and the compiler is open source. So let me quickly show you. I said these attacks that existed in the past are no longer possible. Now, how does the attacker still manage to attack you? So this is code that's legitimately on your machine. It may be signed code. And this is your stack. And now what the attacker does, the attacker overflows the stack, but it overflows the stack not with code, but with data. And then you execute the return. What does return do? Return pops an address on the stack and jumps to it. And what we're going to do is we're going to jump right into something that's legitimately on the machine. And it's just one instruction that loads white. And then there's another return. What does return do? Return pops an address on the stack and jumps to it. And so what the attacker does, the attacker uses all the code that's legitimate on the machine and just builds an attack by just finding code that is followed by a return instruction, and there's lots of that code around. And as a result, the attacker can actually basically has a Turing-complete dictionary of things they can use. And basically, I'm going to have to hurry up a little bit. So this is Microsoft's January to February 2014 report of attacks. You see about 95% of all attacks use return-oriented programming in this way to execute code. The scary thing is that if you look at things, for example, we had a voting machine audit in the US, and during the voting machine audit after the botched 2000 election, basically it was noted that there was an axiom in all these, in the design of these voting machines, that if you couldn't inject code, you couldn't modify the behavior of the voting machines. In light of what we know today about return-oriented programming, all of those audits are completely invalid. So the voting machines were built under the assumption that you can't, inject code. If you can't inject code, that because you have a non-executable memory, then you can't change the behavior of the voting machines. It's kind of scary. So what do you do? Well, so the additional problem is that on x86, for example, you have variable length instructions. So the compiler emitted the code in black, that instruction sequence. But if I jump to it with just an offset of one byte, then I can interpret this as a different instruction sequence. So the attacker has huge amounts of things I'm going to work from. So what we did is we just scanned. We designed a Turing complete set of these little snippets, and you can design many of them, and then we scanned different Linux releases, different programs. Every X means that program all by itself contains a Turing complete set of things you can do with whatever you want. So that's a real problem, right? And if you look at security conferences, like every security conference has a session on ROP right now and how to defeat it. So what do? Well, what you can do is you can create fine-grained diversity. So you can do that by inserting knobs. You can do that by changing the instructions, and you can do that by using code scheduling, which is something the compiler does anyway for performance. But now we're doing it basically to make sure everyone gets a different binary set, because the idea is that the attacker needs to know the locations of these little snippets that they can use. So if every user has a different set, the attack is only going to succeed on a very small fraction of the targets. And even more importantly, the attacker doesn't know which version you have. Right? So right now, we can practice an attack. An attack because everyone has the same binary. Stuxnet was a thing that was targeting people in a foreign country far away, but you can bet that they perfected the attack in a clean room somewhere, wherever it was built. If everyone has a different version, that's no longer possible, because the attacker, short of actually having like the janitor walk in and make and exfiltrate the specific version running there, there's no way that you can do that. And we've been going further. One of the things is the attacker needs to know where these gadgets are that they chose. And what we can actually do is we can actually weave in landmines, and that's what we do now. It's called booby trapping. So in the places where the attacker expects these gadgets to be, we can actually put code that if you hit it, that's code that normally is not part of the application. The compiler wove it in. But if you hit it, then actually we regain control, and we know something happened because this code should not be executing right now. And you can actually react to that. And it's completely automatic. And it turns out that many of the existing attacks that we have out there, we can actually now defend against completely automatically. And it's a very cool idea. So I need to speed up slightly. Let me just quickly say, so we actually have, in my lab we don't build prototypes for little subsets, we build full-scale systems. So we can actually, we have a version for GCC, one for LLVM. We can diversify Firefox, Chromium browser, or complete Linux from scratch. And we actually then, I put my compiler hat back on and say, how do we make this efficient? So we've been able to push the cost down to 1% overhead. So it's perfectly acceptable. And we actually showed this recently at the Black Hat. So we're doing a Windows version now, and we are working on a company spin-out that is going to take the Windows version and commercialize it. So at the university, we're going to keep working on the research part, but this is in the process of being commercialized. And this is already my last slide. So it's not just PCs. It's very interesting. If you talk to the power company, they've gone to these smart meters that are complete, that have no physical moving parts anymore at the side of the house. If one of them gets hacked, then the power company has no idea of who's consuming how much electricity. And they're all the same software. you know, and you have this all over the place that you have the same things, you know, cable boxes, and so on. There's lots of things that if you hack one, you hack every single one of them. Apple is not able to prevent that phone software from being jailbroken. It takes about 2 weeks at the most after the next version of the OS comes out. So, you know, we are probably very soon going to live in a future where the software on every single device is unique, which is just like in biology. There's no accident that evolution produced biological diversity, because it seems to be a good idea in nature. Otherwise, we would all have died of the plague. You know? And so what we're working on is deploy diversity everywhere, including in just-in-time compilation, including everywhere in your stack, and have unique devices everywhere. And so I rushed through this a little bit. Thank you very much. And these are all the people who are funding this right now. Thank you.